We now make a leap into probability. Probability will take statistical information of something that occurred in the past and make predictions based on the results. For instance, we might do a study as to whether parents who were spanked as children when they did something wrong are more or less likely to spank their own children. It should be pointed out that we will be making predictions based on a study. How valid the predictions might or might not be will be studied in the section on inference. 200 parents were interviewed anonymously. We find that 125 were spanked as children, 92 spank their children now if they feel it necessary, and 74 parents were both spanked as children and spank their children now. This information is best described in what is called a Venn diagram. We see two circles, the red spanking kids now circle and the green spanked as kids circle. The two circles intersect, and the 74 parents in both categories are placed in that intersection. Since there were 125 parents who were spanked as kids, and we have already accounted for 74 of them, there are 125 minus 74, or 51 parents in the spanked as kids circle. This 51 represents the parents who were spanked as kids, but do not spank their kids now. Since there were 92 parents who spank their kids now, and we have already accounted for 74 of them, there are 92 minus 74, or 18 parents in the spanked kids now circle. This 18 represents the parents who spanked their kids now, but were not spanked as kids. Finally, since there were 200 parents in the study, and we have accounted for 18 plus 74 plus 51 equals 143 of them, there are 57 parents outside both circles. These represent parents who were neither spanked as kids nor spanked their kids now. Recall that the probability of an event represents the number of ways the event can occur divided by the total possible number of outcomes. We can now answer some simple probability questions by looking at the Venn diagram. The probability that choosing someone who was spanked as a kid is 125 over 200, or 62.5%. The probability that choosing someone who spanks their kids now is 92 over 200, or 46%. The probability that choosing someone who both was spanked as a kid and spanks their kids now is 74 over 200, or 37%. The probability that choosing someone who neither was spanked as a kid nor spanks their kids now is 57 over 200, or 28.5%. The probability that choosing someone who was spanked as a kid but does not spank their kids now is 51 over 200, or 25.5%. The probability that choosing someone who was not spanked as a kid but does spank their kids now is 18 over 200, or 9%. The probability that choosing someone who was spanked as a kid or spanks their kids now, but not both, is 18 plus 51, or 69 over 200, or 34.5%. Notice how all probability questions have a denominator of our total population in our study, 200. We now examine conditional probabilities. These are similar to conditional distributions studied earlier in the slideshow. Condition probability computes the chances that an event A will occur given that event B will occur. It is written as P parenthesis A slash B end parenthesis and read as the probability of A given B. The given condition is B. Suppose we wanted to compute the probability that you spank your kids now given that you were spanked as a kid. The condition is that we were spanked as a kid, and there are 125 parents, those in the green circle, in our study in that category. So the denominator is 125. Of them, there are 74, those also in the red circle, who spank their kids now. So the probability that you spank your kids now, given that you were spanked as a kid, is 74 over 125, or 59.2%. Suppose we wanted to compute the probability that you were spanked as a kid, given that you spank your kids now. The condition is that we spank our kids now, and there are 92 parents, those in the red circle, in our study in that category. So the denominator is 92. Of them, there are 74, those also in the green circle, who were spanked as kids. So the probability that you were spanked as a kid, given that you spank your kids now, is 74 over 92, or 80.4%. Two events are independent if the occurrence of one event doesn't affect the chance that the other event occurs. Some examples of independent events are tossing a coin and getting a heads on the first trial and heads on the second trial. Since the coin has no memory, the results of the second flip have nothing to do with what happened on the first flip. So even if a fair coin was flipped 10 times and we started with 9 straight heads, the chances of a heads on the 10th flip is still 50%. If I draw a red card from a deck of playing cards and then replace that card and choose another card, these events are independent. Since we replace the red card, the probability of choosing a red card on the second trial is exactly the same as the first. Most casino games are independent. Contrary to belief, slot machines have no memory. A slot machine that just hit a large jackpot is just as likely to give a jackpot on the next spin. Two examples of non-independent events are given. If I shoot 2 basketball foul shots, their results are not independent. Even though the ball has no memory of whether it went into the basket, realize that if you are short on the first shot, you shoot harder on the second shot. So the results of the first shot affect the results of the second shot. If I draw a red card from a deck of playing cards and then do not replace that card and choose another card, these events are not independent. If I choose a red card on the first draw, there are fewer red cards in the deck, making it less likely to choose a red card on the second draw. There are two ways to show that events A and B are independent. One is showing that the probability of A given B is the same as the probability of A. That means that the occurrence of B doesn't change the probability of A occurring, which is the definition of independence. A simpler mathematical way of proving independence is showing that the probability of A and B both occurring is the same as the probability of A times the probability of B. We will use that definition in our examples. Using the data from the previous problem, we want to know whether being spanked as a kid and spanking your kids now are independent events. In other words, if you were spanked as a kid, are you more likely to spank your kids now? And if you weren't spanked as a kid, are you less likely to spank your kids now? This can be debated philosophically or psychologically, but we will examine it mathematically, armed with the 200 parents from our survey. We use definition 2. The probability of choosing someone who was both spanked as a kid and spanks their kids now is 74 over 200. The probability of choosing someone who was spanked as a kid is 125 over 200, and the probability of choosing someone who spanks their kids now is 92 over 200. So, since 0.37 is not equal to the product of 125 over 200 times 92 over 200, or 0.2875, we conclude that these are not independent events, that being spanked as a kid influenced whether you spank your kids now. We examine one final problem. Suppose McDonald's is testing a new product to be put in the freezer cases of supermarkets. They call it the iFry. They use 150 people in a blind taste test, and 109 rate the actual McDonald's fry as excellent, 55 rate the iFry as excellent, and 30 people rate both fries as excellent. We want to know two pieces of information. First, are liking McDonald's fries and the iFry independent? And second, McDonald's makes the claim, if you love McDonald's fries, you are going to love the iFry. Is it a valid claim? We first construct the Venn diagram. The 30 people who love both fries are placed in the center with 109 minus 30, or 79, in the only loving McDonald's red circle. 55 minus 30, or 25 people, are in the only loving the iFry green circle. And 150 minus 79 minus 30 minus 25, or 16 people, are placed outside both circles as people who love neither. To test for independence, the probability of choosing someone who loves McDonald's fries times the probability of choosing someone who loves the iFry must equal the probability of choosing someone who loves both. When we multiply 109 over 150 times 55 over 150 and check to see whether it is 30 over 150, we see that 0.266 is not equal to 0.200, so they are not independent. However, they are relatively close in value. The closer in value that they get, the closer to independence we have. So while you can think of the question of independence as a yes-no answer, in reality, independence is thought more on a continuum. And when the mathematics gives values that are close, we might say the two events are mostly independent. The claim, if you love McDonald's fries, you are going to love the I-fry, is a conditional probability statement. It examines the probability of loving the I-fry given that you love McDonald's fries. Since 109 people love McDonald's fries, and only 30 of them also like the I-fry, then the probability is 30 over 109, or 27.5%. So the claim, if you love McDonald's fries, you are going to love the I-fry, appears to be quite false based on this study. The ability of using only 150 people to make claims about an entire population of McDonald's lovers will be examined in the inference section of the course when we examine how confident we are in the claims we make.